Hi students, welcome to the last lecture of this 6th week. This is going to be about heterogeneous equilibria and also other ways in which we might use the equilibrium constant. Just at the beginning, I'm going to say that starting next week, we're going to be doing a lot of things with the equilibrium constant. We'll begin the process of talking a lot about all that can be done with the equilibrium constant. And it's going to get quite involved over the next few weeks. And the math will be, intense, maybe not as intense as the kinetics chapter, but starting next week, the math will get a little bit more intense, I'd say. You're going to be doing interesting things that you haven't done before. So I'll talk a little bit more about that at the end of this video. But I wanted to talk about heterogeneous equilibria now. So for all the reactions that we have taken a look at so far, we've dealt only with gases and a little bit maybe with aqueous substances, not so much, but something's going to happen when we begin to talk about solids and liquids. We kind of touched on it in the kinetics chapter, but the basic idea is that for solids and liquids, the bulk solid and the atoms in it, or the bulk liquid, will generally not all be available to react. And so that's going to seriously affect the rates of both the forward and the reverse reaction and the way in which the amount of solid and liquid impacts the equilibrium. So let's take a look at this reaction here. If you have calcium carbonate limestone, a type of rock, basically chalk, essentially. This can decompose over time into lime, which is the common name for calcium oxide, and carbon dioxide gas. So this is what we would refer to as a heterogeneous equilibrium, because not everything is gaseous here. These two components are solid. And so it turns out that when it comes to the amount of solid that can react, really it's only the solid that's on the surface that is available for this reaction. And so you can have this giant block of limestone, but all that really matters is what surface area is exposed. And so the fact that what basically happens is most of the atoms are unavailable for reaction, and so the amount of atoms that are there does not really affect the rate of the reaction, nor does it affect the equilibrium very significantly. So generally we would write a Kc in this fashion. It would be the products, calcium oxide here, carbon dioxide over the reactants. However, the solids are not going to have an impact on the equilibrium constant. Essentially, what we're going to do is replace these with 1. So basically, this is a simplified version of a more complicated idea called activity. The activity is talking about basically the availability for atoms to even be involved in the reaction. And essentially 99.99999% of the atoms in these solids are not available for the reaction. Only a small number of the atoms that are on the surface are even available. So the result is that the amount of these reactants and products that are solid really doesn't matter and doesn't affect the rates of the forward or the reverse reaction, and thus it doesn't affect the equilibrium constant. The only substance here with all of its molecules available is the CO2, because it's gaseous, and so those molecules can be flying all over the place. So the result is that the K for this reaction excludes the solids and only includes the gas. And that's what it's going to be like in heterogeneous equilibria. So when we're writing equilibrium constant expressions, we only include those substances which are gases or aqueous. We do not include substances which are solid or liquid, because those are only available to react on the surface or the interface of these heterogeneous equilibria. So pure solids and liquids are not included in the equilibrium constant expression. So be very careful. This is also true for rate constants as well, although we didn't focus on it that much. Only only gases and aqueous substances where all of the molecules are always available to react does the concentration matter. For solids and liquids where they can only react on the surface, the amount doesn't really matter because most of those atoms and molecules are not available to even react, so that they don't affect the reaction in any way. So if we're writing the Kp for this reaction, we'd only include the product concentration here for CO2. If we're writing the Kp, we'll only include the pressure of the gas CO2. In both of these types of Ks, we do not include pure solids or liquids because most of their atoms are not available for the reaction. So here's an example of this same reaction. So we have piles here of the solid calcium carbonate reactant and pile of the solid calcium oxide product. And it doesn't matter if we have a lot of product, calcium oxide product, and a lot of calcium carbonate reactant, or if we have a bigger pile of the calcium carbonate reactant and a smaller pile of the calcium oxide product. In both cases, the equilibrium expression, let's write it in terms of Kp, is the pressure of the CO2 only. It does not matter the size of this pile. Why? It's because the fraction of these atoms that are on the surface is only a tiny fraction of all of those that are available in the pile. And so changing the size of the pile does not significantly change the number of atoms that are available for reaction. And so it does not affect the equilibrium in any way, really. It does very, very slightly, but so slightly that we ignore it, basically. You know, so what if you have double the atoms on this bigger pile than the other one, smaller pile? The 99.99999% of those extra atoms cannot react at all, and so it doesn't affect the equilibrium. You can see that the pressure of CO2, which is equal to the equilibrium constant in this case, is the same no matter how much of the calcium carbonate or calcium oxide are present. And so the take-home message here is that equilibrium constant expressions exclude pure solids and liquids. They only include aqueous components and gaseous components because their atoms and molecules are completely available to react. So if you double the amount of carbon dioxide molecules here, or the pressure of the carbon dioxide, you have doubled the amount of carbon dioxide available for reaction. But if you double the size of the pile here for calcium carbonate, you've essentially, in terms of the fraction of atoms that are there, you have not changed how many are available to react very significantly at all. So that's a statement on heterogeneous equilibria. Again, only include gaseous or aqueous in your case. Now, what does the K mean for us? Why do we care about the K? Well, the size of the K tells us something about how much products and reactants we're going to have at equilibrium, which is super important if you're running reactions that you're trying to produce products, right? So let's say we wanted to do a reaction where we take water and we split it into hydrogen gas and oxygen gas. This would be a super useful reaction, right? Because if we have hydrogen and we put it in a tank, later we can burn it with oxygen and get energy out. And so that's in fact how the space shuttle used to take off. Hydrogen, one big tank of hydrogen, one big tank of oxygen. You burn it and it goes backwards here and you get pure H2O. However, pushing this reaction forward is extremely difficult. The equilibrium constant is so tiny. What this tells you is if you just have a pile of water sitting there, it's going to be almost all water, right? Because remember, the K is, very roughly speaking, products over reactants. So a very small K means you've got a lot of reactants and not a lot of products. You have, in this case, K is so small, you have very, very little products and a whole lot of reactants, meaning K is very small. When K for a reaction is small, that tells us it's going to be a very difficult reaction to get any products out of. And we're going to have to use all kinds of measures to try to force it in the forward direction. How can you force a reaction in the forward direction? We'll talk about that next week. But this is just to say, if you're trying to evaluate a reaction that you actually want to do, the equilibrium constant tells you a lot. Here it tells us, because it's so small, it tells us we're not going to get a lot of products. And so this is not a reaction that's going to be very useful for us, probably. What about for Ks that are close to 1? So they're in the middle. And so the kind of rough range is somewhere between 10 to the minus 3 and 10 to the third is we'll consider close to a K of 1. This means that when we get to equilibrium, we'll have a significant amount of both products and reactants. If they were exactly equal, we would have a K of around 1. So here, this K is 57, meaning we'd have a little bit more products than we have reactants here. However, not by much, right? So here, this kind of reaction, sure, this would be an okay reaction. We could perform this reaction and get HI out of it. Wouldn't be fantastic, but we'd definitely get, some products out. Whereas for another type of reaction, so this is the reverse basically of the other reaction, hydrogen reacting with oxygen to make water, this will go completely to the right. This will really just, these will burn up and they'll make all water, and by the time you're done, you'll have almost no hydrogen and oxygen. So this is a reaction that would be very easy to run. It would produce a lot of products here, and we'd have almost no reactants left. That indicates a big K. That tells us at equilibrium we got tons of products, but not a lot of reactants. And so K tells us how far the reaction will go and what is the amount of products versus reactants that we'll have at once the reaction has stopped, essentially. So again, this is not something you want to memorize. This is something you want to understand. If you have a K that is big, and let's say bigger than 1,000 or so, products predominate over reactants at equilibrium. We've got lots and lots of products once we get to equilibrium. If K is smaller than 1/1000th, 10 to the minus 3, this means we get very little products. We have mostly reactants left over when the reaction has appeared to stop. And if K is somewhere in between these, somewhere between 1,000 and 1/1000th, we'll have a pretty significant amount of both reactants and products. This is a serious issue too. I know some of you guys are interested in in being doctors or in the healthcare field. When it comes to pharmaceutical drug production, many equilibrium constants are in the middle here, which means that you have a lot of the reactants left over that may be toxic to people. Okay, the drug itself that you're producing may be beneficial, but whatever reactants were left over, for example, sulfuric acid, very commonly used to catalyze these reactions, battery acid as they also call it. Lots and lots of organic reactions use this, but you don't want to leave sulfuric acid in there with your drug product. And so evaluating this K also tells us how much reactant we'll have left over. And in the pharmaceutical industry, that's really important because you have to find a way to remove those before you have a final drug product. And in many industrial reactions, this is true as well. Finally, what can we do with the equilibrium constant? Okay, well, we had an example previously where we calculated the equilibrium constant, but what if we're given the equilibrium constant? First of all, let's evaluate this. This equilibrium constant is slightly less than 1, which means we'll have significant amounts of both products and reactants at 1,000 degrees Celsius when this is at equilibrium. Slightly more reactants than products because this is slightly less than 1 in terms of pressures anyway. And it says at equilibrium, the partial pressure of hydrogen is 1.22 atmospheres. What is the equilibrium partial pressure of methane? Well, first of all, we should write a Kp expression. So we write Kp. Oops. So we write a Kp expression here. And notice here, the carbon is solid, so we're not going to include it. We're going to include the product pressure of the CH4, also called methane, and we're going to divide that by the pressure of the hydrogen squared. And we're not going to include the carbon because it's solid, so it's not included in the equilibrium constant expression. Now we're asked for the partial pressure of the methane, so to solve for that, what we can do is we can multiply both sides by the pressure of the hydrogen squared. That will cancel here, and what we'll get is that the pressure of the methane equals Kp times the pressure of the hydrogen H2 squared. Okay, so now we simply need to plug in these values. And again, we're dealing with K's, so you don't have to worry too much about units. So we'll just plug in the numbers, 0.262 for the Kp, and then for the pressure of the hydrogen, it will be 1.22, and we'll square that. And so we'll get the pressure of the, you should pay attention to what the units are in here for the final answer, because you'll want to know, what were the pressure units? The pressure units were in atmospheres, as they generally are for these equilibrium constants. And or the pressures rather that you put into the equilibrium constant expression. So now let's calculate it. 0.262 times 1.22 squared, and we get a pressure of, to 3 sig figs, 0.390. Oh. 0.390 atmospheres. And so if we are given the equilibrium constant and the pressures or concentrations of the other components at equilibrium, we can determine whatever component we don't have the pressure or the concentration of. And so that's another way that we can use the equilibrium constant. Now, next week, we're going to start to study problems where you will be given only the K and asked to determine the equilibrium concentrations of all reactants and products. And you'll be given, a starting concentration. So this was an equilibrium concentration, right? So next week, you'll be given the K and some starting concentration. So not at equilibrium. So this is next week. Not equilibrium. And you'll have to figure out the concentrations of everything. And this will be a bit more mathematically involved. We'll have to make assumptions to simplify the math. This is probably going to be the first week that you have ever had to, or the first time you have probably ever had to make assumptions in order to finally complete the math to describe the science that you're learning. It generally does not happen in your physics class or biology classes. It will happen in your higher level mathematics and higher level physics and chemistry classes. So this is usually students' first introduction to making assumptions that simplify the mathematics, and in some cases are the only way to make the mathematics solvable. And so make sure to study the homework this week and do the homework, but also start to be looking a little bit ahead to next week, I'd say, because like I said, next week is going to be a little bit more intense. I know it's only 2 sections, but those 2 sections are the real meat of the chapter. So this week was the kind of introduction to equilibrium constants, doing a little bit of the math. The real meat of the chapter will be next week, so there'll be less lecture, but there'll be more practice. You'll want to do lots of problems and practice. So a lot of my lecture for next week will not be talking about theory. It will be talking about practical ways to complete problems. We'll go through a lot of different problems, and that will be the majority of what I lecture on next week. So that's going to be it. for our introduction to equilibrium for this week. Make sure to read your textbook. The first, I can't remember it right now, but the first several sections, it's in your syllabus. I think it's 17.1 to 17.4. Let me look here. Yeah, it's our 17.1 to 17.4, right. And then next week we're going to be doing 17.5 and 17.6, which, as I said, is going to be a little bit tougher, but it's going to be the foundation for what we are studying as we move forward. So you definitely want to put in the time now so that the future of this class will be easier for you. So, if you get done with all your work this week, I would highly encourage you to go through and read through to the end of chapter 17 if you have any extra time later this week, and start to get ready for that and to look at the examples in there. So until office hours, I'll see you guys later, and happy studying. All right, see ya.